In this video, we're going to use a while loop to implement the bisection method. So what exactly is the bisection method? Well, the bisection method is a method for finding the zeros or roots of a continuous function, where that's just a fancy way of saying where the function equals 0. So we have a continuous function and we want to find where that function equals 0. One of the basic requirements for the bisection method is that when we start our algorithm, we have to start by choosing two values initially such that the function evaluated at those values has opposite signs. So when we start for one of the values, the function will be less than 0. The value of the function at the other starting value is going to be positive. So let's start off by assuming that we have a continuous function f of x. So how do we go about implementing the bisection method? To start off, we have 2 points A and B, and let's assume that A is less than B for simplicity. And we want to start our bisection algorithm off by ensuring that f of A times f of B is less than 0. The reason we do this is because if f of A times f of B is less than 0, it means that when we evaluate f of A and f of B, one of them is positive, and then the other one is negative, which is what we require in order to implement the algorithm. Assuming that condition is satisfied, we next compute the average of A and B. So we compute m equal to A plus B over 2. And at this point, we need to decide whether we should stop our algorithm or not. We compute f of m, take the absolute value, and compare that to epsilon, where epsilon is some really small positive number like 0.0001. If that condition is satisfied, so if this condition is true, it means that we have not found a root. We have not found a 0 for our continuous function, and we need to keep going in our algorithm. So if we haven't found a root yet, if f of m times f of a is less than 0, then that means a root exists between a and m. So we set b equal to m, and then return to step 2 up above. If that's not the case, if f of m times f of a is greater than 0, that means a root exists between m and b, in which case we should set a equal to m and then return to step 2. And we keep doing this over and over and over again, with m getting closer and closer to the root of our function, until eventually the absolute value of f of m will be less than epsilon, in which case we have found an approximate root of our continuous function. So we're going to create a function called bisect that implements the bisection method. The function is going to take 2 arguments, lower, which is the lower starting value used to implement the bisection method, upper, which is the upper starting value used to implement the bisection method. The bisect function will also take the argument fun, which is a continuous function that can take both positive and negative values, and then eps, which stands for epsilon, which is a tolerance value indicating how close we must be to a true 0. So here is our implementation of the bisection method. So we have our function, we're going to call it bisect. We have the lower argument and the upper argument. We have the fun argument. And by default, we're going to set EPS, epsilon, equal to 0.0001. So we want to make sure that our function, when we evaluate it at m, is less than or equal to 0.001. We know that when we evaluate our function at the lower and upper values that it has to take different signs. And so the first thing that we do in our algorithm is actually check that that's satisfied. So we compute fun of lower, so we evaluate our function at the lower bound. We multiply that by our function evaluated at the upper value. And if that value, if that product is greater than 0, it means we don't have opposite signs like we need, and we actually are going to throw an error. So our function will stop and will not proceed. So here we use the stop function to generate an error to make sure that we stop and that we don't try to implement or apply the bisection method when it's not appropriate. But assuming that our condition is satisfied, then we compute m. So we have lower plus upper divided by 2. And now we can implement our while loop. So we evaluate our function at the value m. We take the absolute value because in case it's negative, we want to account for that possibility. So we take the absolute value of our function evaluated at m, and we ask, is that value greater than epsilon? If it is greater than epsilon, it means that we're not close enough to a root or to a 0. So then next, we need to decide where we need to go in our algorithm. And so if our function evaluated at m multiplied by our function evaluated at lower is less than 0, which means that the root is below m, we set upper equal to m. Otherwise, it means that we're in the other scenario and we set lower equal to m. So now that we've decided which case that we're in, we need to determine a new candidate value for m. And so we average lower and upper by adding them together and dividing by 2. So we get our new value of m. And then we go to the top of our loop. We ask whether when we take the absolute value of our function evaluated at m, it's greater than epsilon. If it is, we keep running this. And so we keep doing this over and over and over and over again until eventually, when we evaluate our function at m and take the absolute value, it's going to be less than epsilon. And we will, at that point, we exit our while loop and we're going to return the value of m, because that's going to be at least an approximate 0 or root for our continuous function. So let's run this in order to get it into R's memory. And let's apply our bisection algorithm to the continuous polynomial function f of x equals x minus 3 and x plus 1. If we just look at this function, it's pretty easy to see that f of x is equal to 0 when either x is equal to 3 or x is equal to negative 1. So what we're going to do is we're going to create that function in R. So we call our function f, it's a function of x, and then the function returns x minus 3 times x plus 1, which is what we have up here. So we run that to put it into R's memory. And just to verify what's going on with our function, we're going to create a sequence of values between negative 2 and 4 of length 1000, and we're going to plot our function. And so we can see that our function is going to be 0 here, and then also here. So when x is equal to negative 1, and also when x is equal to 3. Now we're going to try to find a root of f using our bisect method. And we're going to start at values of 2 and 5. So when we look at 2 here, that's negative. And we look at 5, we can see that f of 5 is going to be above 0. And so when we run that, we get an approximate root. We get an approximate root of 2.99999. Okay, so basically it's 3, right? So it's not exactly 3, but it's really close. And if we choose different starting values, if we'll start our algorithm at negative 2, where f is positive, and then at x equal to 1, where f is negative. So our condition is satisfied. We run our bisect algorithm again, and we get negative 1.00002. And so once again, this is really close to the true value of negative 1, but it's an approximation because this is a numerical algorithm and not an analytical one. You may be wondering, well, what happens if we choose bad starting values? So we're going to start our bisect algorithm, our bisection method at negative 4 and 5, where f is positive for both of those values. And when we do that, we get an error. So it tells us that basically we can't use those starting values and we need to choose different starting values instead.